Not number one. In N-type semiconductor, the majority carrier is the electrons. That is the electrons. And the minority carrier that is the holes. Second.
8 o'clock.
In N-type semiconductor, the number of electrons in N-type semiconductor number of electrons is greater than the number of holes. And we know the velocity of electron is greater than the velocity of hole. Therefore, IE is greater than IH. I is almost equal to IE, where IH is negligible. Third, N-type semiconductor is shown in diagrams as follows. So we can symbolically show the N-type semiconductor as a block with electrons, free electrons that we denote with dots, or we can show it as a block with minus. Still, the number of protons is equal to the number of electrons in an N-type conductor, in N-type semiconductor. Therefore, it is electrically neutral. Therefore, it is electrically neutral. Although we say N-type, negative type semiconductor, it is actually electrically neutral. Is the final point clear? That they are electrically neutral. The final point, don't write what I am writing now. I'll just explain. Now let's say we have a silicon lattice. This silicon lattice is electrically neutral. No doubt about that. Okay, it is electrically neutral. What we're going to do is we're going to add a phosphorus atom to this. When I add a phosphorus atom, now this phosphorus atom has 5 valence electron. So let's say it replaced this silicon Now this has 5 valence electron. That means there is one additional electron. Okay, there is one additional electron which makes us feel that it has to be electrically negative. But the real idea is, before we add, it was electrically neutral. Now, when we are adding this phosphorus is the 15th element, right? Then this will have 15 protons and 15 electrons. So when I add this into this lattice, it will take those 15 proton and 15 electron together. So actually, it is not creating any additional charge. It is not creating any additional charge. So it remains electrically neutral. Is that idea clear? Those who got, can you raise hand? Or if anyone has any doubts with that, you may ask. If you still didn't get the idea of the fourth note. So second, P-type semiconductor. To make a P-type semiconductor, we will have to introduce group 3 element. Group 3 element has only 3 valence electron. Therefore, when it forms bond with silicon, it is always deficient with 1 electron. So the 3 electrons forms bond, but one of the bond is deficient of an electron. Due to this, number of holes increases in relative to number of electrons, which will create a vacancy. Due to this vacancy, electron will start to move. Due to this vacancy, electron will start to move, which will in turn create increase the electrical conductivity. So this is a hole. So here, group 3 element is doped at the ratio 1 boron is to 1 million silicon. The doping ratio might differ according to the need, but the general is this value. Okay, the general value is this. 3 valence electrons of the group 3 element forms 3 bonds, and the fourth bond is deficient of an electron. Thus, this creates a hole. Now, group 3 elements, they are not donating electron, they are accepting electron. So they are known as acceptor atoms. Since group 3 elements accept electrons. They are called as acceptor atoms. Acceptor atoms. Not number one. In p-type, the majority carrier is the holes, and the minority carrier is the electrons. In p-type semiconductor, although number of holes is greater than the number of electrons, still velocity of electron drift velocity of electron is greater than the drift velocity of hole. Therefore, IE is greater than IH. IE is greater than IH. Therefore, I is almost equal to IE. Although number of volts is greater, still the current due to electron flow is significant. Okay. We can denote p-type semiconductor. P-type semiconductor are shown in diagram. As holes or positives. Just like n-type semiconductors, p-type semiconductors are also electrically neutral. Electrically neutral. So, so far, all good, right? We are starting a new subtopic, junction diode. Junction diodes. Up to now, I are clear. Okay. Now I will explain how a junction diode works. Okay, now I'll explain how a junction diode works. After that, let's write the note. So first I'll explain, everyone. Look closely. First, we have a p-type semiconductor and an n-type semiconductor separately. So this p-type semiconductor and this n-type semiconductor, both of them are made in a single block. Both of them are made in a single block of semiconductor. That means they are joined together, just like this. Just like this, they are joined together. When they are joined together, on this side of this junction, we have more holes. On this side, we have more holes. This is p-type. This is p-type. And on the other side, we have n-type. So this side has more holes and this side has more electrons, more free electrons. So what happens is, these free electrons, what is holes? Holes is the absence of electrons, right? So these electrons now move across this junction, to fill these holes. They move across this junction to fill these holes. But as they move across this junction, something else also happens. When they do this, here, already this p-type and n-type were electrically neutral. These two sides were electrically neutral, but this time when the electron starts to flow to the other side, this side now becomes electrically positive. This region starts to become electrically positive. This side becomes electrically positive. And on the other side, we had equal number of protons and electrons. They were electrically neutral. As these electrons diffused into the p-type region, this side now becomes electrically negative. So an electric field is set up. Gradually an electric field is developed in this region, in this direction. So now these electrons cannot diffuse from one region to the other. For example, let's say some of the electron, an electron got into this region. Then, due to this electric field, the electron gets pushed back into this n-type region, right? At the same time, here you don't have any electrons or holes. If you had so, let's say you had a hole over here, then due to this electric field, it gets pushed into this region. And if you had an electron, it gets pushed into this region. So there is no free electron or holes. Therefore, we call this region as depletion layer. This region, we call it as the depletion layer. We can call it as the depleted region or as the depletion layer. So, is the idea clear? What is happening? Why a depletion layer is formed? And very important, these uh, polarities. Why this side is positive? Why the N-type side is positive and why the P-type side is negative? And what is the direction of the electric field? Are they clear? Okay, shall we draw those two diagrams quickly? Once you have drawn those diagrams, write this also. So here, junction made by P-type and N-type semiconductor kept in contact is called the junction diode. Soon as the junction is made, the majority carriers diffuse across the junction. After some time, due to excessive electrons in the P region and electron deficiency in N region in the in the N region, these regions gain negative and positive charges respectively. Negative and positive charges respectively. This setups an electric field which obstructs furthermore movement of majority carriers across the junction. Once you have noted, let me know. Finished copy. So we discussed this point also. And not write this down. Note number 1. Note number 1 and note number 2. So you have completed, And so here we have mentioned that minority carrier can cross the junction. So think on this side, on p-type, the majority is holes, but there might be, there are free electrons. So when a free electron gets to this junction, it is automatically pushed to the other side, right? So the majority carriers cannot cross this junction, but the minority carriers, they can cross this junction. Similarly, if you have a hole on this side, on the n-type side, hole is minority carrier. When they come to the junction, they are taken to the other side. Okay. So the minority carrier can cross the junction. Done. There with the first note, right? That minority carriers can diffuse. Only the majority carriers are blocked. Copy the remaining also, 3, 4, 5. So we discussed, right, that an electric field will be set up. When there's an electric field, there will be a potential difference. That potential difference, we call it as the barrier voltage, okay? So this barrier voltage will depend on the amount of doping and the temperature. Because depending on the temperature only, how much of electrons, or depending on the doping and depending on the temperature only, it decides how much of electrons initially diffuse before this barrier is strong enough to stop them. Okay. Usually the barrier voltage of silicon is from 0.6 to 0.7, and for germanium it is from 0.2 to 0.3. Copy these three. Done. Okay, the meeting will end now. Join after the when I start, okay? It will take around 2 minutes.